Hello. In this video, we will give a guide and tips for chapter 28 of my Java book. Beginning from this chapter and next chapter, we introduce graph algorithms and graph applications and develop data structures for modeling graphs. Graphs are very useful mathematical model. They can be used to solve many things. For example, if you use Google Map, you find the shortest distance from one location to the other, and that involves graph algorithms and data structures for graphs. So, and this is example of a graph, a simple map, and with all these major cities and the lines and can represent a flight connecting to the cities and all the highways. So this is just hypothetically, we have the flights from Seattle to Denver, but actually we have flights from Seattle to Miami, but it's just for simplification. We assume that this is only, you have Seattle, you have the flights from Seattle to Chicago, Denver, and San Francisco. So you may ask the question, what is the minimum number of flights, or the stops from Seattle to Miami? So to answer this question, and you can use the graph algorithm to help you solve it. So here and now we have this section on the basic graph terminologies, and this is an animation to show some common graph applications. Representing graph. How do we represent a graph? Representing graph consisting of vertices and edges. So we represented the vertices using an array, and actually the better is to use an array list. That's more flexible. You can add and remove vertices easily from an array list. So for simplicity here, we just say this is vertices, a list of the array of strings, and it can be any type, object type. So here, for example, we have a city. So we may have a list of the cities. So this is the city, each city is an object. So this is the illustration here. You have the indexes associated with all the vertices internally, and that's a better representation. So it's easy to access the vertices just through the indices. So representing edges. So we can represent using edges using edge array. So this is the means there's edge from 0 to 1. So the vertex corresponding to index 0 and to 1, and 0 to 3, 0 to 5, and here's 1 to 0. So this is both ways. And representing edge using edge object. So this is our edge object representation. And so this is here, and we have this is the override of the equals method, and for this this is put two edges here. So this is the edge object, edge. So this is the edge here. So representing edge, and from vertex at index u to v. So we can now add this edges into array list. So here's the array list. We add the edges here. And there's another way to represent all the edges using adjacency matrix. So here's the square matrix. You have, so 1 means there's edge from Seattle, and 2 San Francisco. And so here's 1 from Seattle to Denver. So here, this is all this, the 0 means there's no edge. So corresponding between the two cities. So this is and the adjacency matrix. So we can represent it, the edges using adjacency list here. Adjacency list here, we have this all the neighbors here, and all the neighbors of 0, the vertex at index 0. So this is all this vertices. And there's a more flexible way is we have this is using put an edge right the objects. So this is neighbor 0. So there's 0, 1, 0, 3, 0, 5. So these are all the edge objects. All right, I think most flexible way is we're going to use this. So you can add more information to the object's edge. So now this is the design. So we designed this as the weighted here, the weighted graph. So this is the weighted graph. It's a subtype of unweighted graph, and it's subtype of graph. Graph is interface. So here we're going to talk about the weighted graph in the next chapter. Now we focus on this unweighted graph. So here, what is in graph here in general? So these are all the things we have in graph. You get the size, number of vertices, and get all the vertices, and get a vertex using specified index. So you get the index for the specified vertex. So this get all the neighbors. So there's many methods you can add and remove vertex edges, and you can perform a depth first search and a breadth first search, so and so on. And here, this is the test program. Suppose we have all this designed, implemented, and so now we write a test program, get used to the graph interface and unweighted graph class. So this is to do a test here. And so this is the complete code for the graph interface and for the unweighted graph implementation. So this is here. And next, and let's visualize the graph. So we have the graph vertices and edges. So it's really nice and to see the graph visually. So we're going to see the graph visually, and by writing this the graphic code here. So this is the one here. We're going to display all the graphs and all the vertices and edges. And traversal. How do you traverse all the vertices on the graph? So we're using depth first search and breadth first search. So we're going to look at the depth first search as you start from vertex and go all the way as deep as you can, and then go backtrack and continue, and then backtrack, continue. So that's called a depth first search. So this is the depth first search, and that is the one we already implemented in the unweighted graph class. So now we tested the depth first search. And it's a tree. What do you get at depth first? The result is a depth first search tree. So the depth first search, there's a lot of good applications of depth first search. So many of this, and so look at the section here, applications on the DFS. And here's a case study on this using depth first search, and to find the orders, the circles are connected. So you can write a code. If they're all connected, we have one color for all this. If they're not connected, so there's no solid color. So that's the application, and for the connected circle problem. And this, now the breadth first search. The breadth first search, you start from vertex and you traverse it, and then traverse all the neighbors and neighbors. So this is level by level. This is the breadth first search. And breadth first search is implemented. We use a queue to implement it. So this is the algorithm. And so here's already we implement it in the graph, the unweighted graph class. So this all here, and now you can see this, the test code, and this is the example here. And so now we go to this application for the 9 tails problem. So here's 9 tails, and you're gonna flip the 9 tails of head and heads and the tails. So you flip to get everything to become tail. When you only can flip the head, when you flip the head, you flip the cell and also its neighboring cells. So you click on this, and so you flip here this, and you click on this, you flip. Now everything is tail. So that's what we need to do to find the minimum number of clicks and to flip everything to the tail. So this is the interesting problem, and we can solve it by reducing it to a graph problem, using the graph model to model it and becoming a shortest path problem. So that is the 9 tails problem. Well, that is all for this chapter on unweighted graphs. Next chapter will introduce weighted graphs. Thank you for watching. Goodbye.